Myself, Dr. Sachin Kumar, welcome you in lecture series of Module 3 Differential Calculus 2nd. Topic of my today lecture is Taylor's and Maclaurin's theorem for function in one variable. In this lecture, I will discuss about Taylor's theorem for function of one variable, Maclaurin's theorem for function of one variable, and problems of application of Taylor's and Maclaurin's theorem in series expansion of function in one variable. So let us start with Taylor's theorem for function of one variable. If y equal to fx be a function in single variable x and all its derivative up to desired order be finite and continuous for value of x lying in range x greater than or equal to a less than or equal to a plus h, then fa plus h can be expanded in an infinite series of form fa plus h equals to fa plus 1 over factorial 1 h f dash a plus 1 over factorial 2 h square f double dash a plus 1 over factorial 3 h cube into f triple dash a, and so on. Equation 1 represent Taylor series expansion of fa plus h in powers of h. Taking a plus h equals to x or h equals to x minus a in equation 1, we get expansion of fx equals to fa plus 1 over factorial 1 x minus a into f dash a plus 1 over factorial 2 x minus a whole square into f double dash a plus 1 over factorial 3 x minus a whole cube into f triple dash a plus up to so on. Here equation 2 represent Taylor series expansion of y equal to fx about the point x equals to a or in powers of x minus a. Again replacing a by x in equation 1. We get, that is, if we replace a by x in this equation 1, we shall get expansion of fx plus h equals to fx plus 1 over factorial 1 h f dash x plus 1 over factorial 2 h square f double dash x plus 1 over factorial 3 h cube f triple dash x plus up to so on. Equation 3 represent Taylor series expansion of fx plus h in powers of h. Now Maclaurin's theorem for function of one variable, taking a equal to 0 and replacing h by x in equation 1. That is, if we take a equals to 0 and replace h by x in this equation 1, we shall get expansion of fx equals to f0 plus 1 over factorial 1 x f dash 0 plus 1 over factorial 2 x square f double dash 0 plus 1 over factorial 3 x cube f triple dash 0 plus up to so on. This is known as Maclaurin's theorem, and series expansion represented by equation 1 is known as Maclaurin's series expansion of y equal to fx in powers of x. In other words, we can say that Maclaurin series is same as Taylor series expansion about x equals to 0. Example: expand sin x in powers of x up to the fifth derivative terms. Solution: as we know that for any function y equal to fx, we have fx equals to f0 plus 1 over factorial 1 x f dash 0 plus 1 over factorial 2 x square f double dash 0 plus 1 over factorial 3 x cube f triple dash 0 plus up to so on. So from equation 1, we observe that this is nothing but Maclaurin series expansion of fx in powers of x. So in order to expand sin x in powers of x, we require to use Maclaurin's theorem. So for this we take fx equals to sin x such that f0 becomes 0, sin 0 is 0. Also on differentiating equation 2 with respect to x, we get f dash x equals to f dash x is obtained by differentiating this with respect to x. So derivative of sin x will be cos x. We shall get f dash x equals to cos x. Putting x equal to 0, we get f dash 0 equals to 1. Similarly, if we differentiate f dash x again with respect to x, we get f double dash x equals to minus sin x. Derivative of cos x equals to minus sin x. So putting x equals to 0, here we get f double dash 0 equals to 0 as sin 0 is 0. Now if we differentiate f double dash x again with respect to x, we get f triple dash x equals to minus cos x, and putting x equals to 0, we get third order derivative at x equals to 0 equals to minus 1. Differentiating third order derivative term, again with respect to x, we get fourth order derivative of f equals to sin x. Putting x equals to 0, value of fourth order derivative at x equals to 0 will be 0. Now differentiating fourth order derivative with respect to x, we get fifth order derivative equals to cos x, as derivative of sin x will be cos x. And putting x equals to 0, we get value of fifth order derivative at x equals to 0 to be 1. So if we put all these values in equation 1, we get expansion of sin x equals to f0. f0 is 0 plus 1 over factorial 1 into x, value of f dash 0 plus 1 over factorial 2 x square into value of f double dash 0 plus 1 over factorial 3 x cube into value of third order derivative at x barabar 0, that is which is minus 1, plus 1 over factorial 4 x4 into value of fourth order derivative which is 0, plus 1 over factorial 5 x5 into value of fifth order derivative at x equals to 0 which is 1. So simplifying, we get sin x equals to x minus 1 over factorial 3 x cube plus 1 over 5 x5 and so on. Next example, expand fx equals to cos x about the point x equals to pi by 4. We know that Taylor series expansion of a function about any point x equals to a is given by fx equals to fa plus 1 over factorial 1 x minus a into f dash a plus 1 over factorial 2 x minus a whole square into f double dash a plus 1 over factorial 3 x minus a whole cube into f triple dash a and so on. So to get expansion of fx equals to cos x about x equals to pi by 4, we take a equals to pi by 4 in this equation. Now since fx equals to cos x, putting x equals to pi by 4, we get value of f pi by 4 equals to cos pi by 4 which will equals to 1 by root 2. Also if we differentiate equation 2 with respect to x, we get f dash x equals to derivative of cos x minus sin x. Putting x equals to pi by 4, we get f dash pi by 4 equals to minus 1 by root 2. If we differentiate f dash x, again with respect to x, we get f double dash x equals to minus cos x, and putting x equals to pi by 4, we get value of f double dash pi by 4 equals to minus 1 by root 2. Again differentiating second derivative term, we get third order derivative equals to sin x, as derivative of cos x is minus sin x and minus minus will become plus. We shall get f triple dash x equals to sin x. Put x equals to pi by 4, we get value of third derivative at x barabar pi by 4 to be 1 by root 2. Differentiating third order derivative, again we get fourth order derivative equals to cos x. Put value x equals to pi by 4, we get value of fourth order derivative at pi by 4 equals to 1 by root 2. And differentiating fourth order derivative, again with respect to x, we get fifth order derivative equals to minus sin x. Put x equals to pi by 4, we get value of fifth order derivative at pi by 4 equals to minus 1 by root 2. Now putting values of all these derivatives in equation 1, we get expansion of cos x equals to 1 by root 2 plus 1 upon factorial 1 x minus pi by 4 into value of first order derivative at pi by 4 plus 1 by root 2 into x minus pi by 4 whole square into value of second order derivative at pi by 4 which is minus 1 by root 2 plus 1 over factorial 3 x minus pi by 4 whole cube into value of third order derivative at pi by 4 plus 1 over factorial 4 x minus pi by 4 whole power 4 product with fourth order derivative at x barabar pi by 4, and in the last term 1 over factorial 5 x minus pi by 4 whole power 5 into product with fifth order derivative at pi by 4 which is minus 1 by root 2. Simplifying, we get cos x equals to 1 by root 2 can be taken common from each term. So we get cos x equals to 1 by root 2. Inside the bracket, we get 1 minus 1 over factorial 1 x minus pi by 4 minus 1 over factorial 2 x minus pi by 4 whole square plus 1 by factorial 3 x minus pi by 4 whole cube plus 1 over factorial 4 x minus pi by 4 whole power 4 minus 1 by factorial 5 x minus pi by 4 whole power 5 plus up to so on as required Taylor series expansion. Next example, expand sine pi by 4 plus h in powers of h. By Taylor's theorem, we know that expansion of fa plus h is given by fa plus h equals to fa plus 1 over factorial 1 h into f dash a plus 1 over factorial 2 h square into f double dash a plus 1 over factorial 3 h cube into f triple dash a plus up to so on. So to get desired expansion, we take a equal to pi by 4 and fx equals to sin x, such that equation 1 reduces to f pi by 4 plus h equals to f pi by 4 plus 1 over factorial 1 h into f dash pi by 4 plus 1 over factorial 2 h square into f double dash pi by 4 plus 1 over factorial 3 h cube into f triple dash pi by 4 and so on. Now fx equals to sin x, putting x equals to pi by 4, we get f pi by 4 equals to sin pi by 4, which is equal to 1 by root 2. Differentiating fx with respect to x, we get f dash x equals to cos x. Putting x equal to pi by 4, we get f dash pi by 4 equal to cos pi by 4, which is equals to 1 by root 2. Again differentiating f dash x, we get f double dash x equals to minus sin x. Putting x equals to pi by 4, we get f double dash pi by 4 equals to minus sin pi by 4 equals to minus 1 by root 2. Differentiating second derivative again with respect to x, we get f triple dash x equals to minus cos x, and putting x equals to pi by 4, we get f triple dash pi by 4 equals to minus 1 by root 2. Putting all these values in equation 2, we get expansion of sin pi by 4 plus h equals to 1 by root 2 plus 1 by factorial 1 h into 1 by root 2 plus 1 over factorial 2 h square into minus 1 by root 2, which will be the value of second order derivative of given function at x barabar pi by 4 plus 1 by root 3 h cube into minus 1 by root 2, value of third order derivative at x barabar pi by 4 and so on. Therefore, on simplification and taking 1 by root 2 common, we get sin pi by 4 plus h equals to 1 by root 2. Inside the bracket we have 1 plus 1 over factorial 1 into h minus 1 over factorial 2 into h square minus 1 over factorial 3 into h cube plus up to so on. Next example, expand fx equals to log 1 plus x in powers of x minus 1. As we know that Taylor series expansion of a function about any point x equals to a is given by fx equals to fa plus 1 over factorial 1 x minus a into f dash a plus 1 over factorial 2 x minus a whole square into f double dash a plus 1 over factorial 3 x minus a whole cube into f triple dash a plus up to so on. So we take a equals to 1 in this question and fx equals to log 1 plus x base a. Now fx equals to log 1 plus x, putting x equals to 1, we get value of f1 equals to log 2. Also differentiating equation 2 with respect to x, we get f dash x, derivative of log 1 plus x will be 1 over 1 plus x. Putting x equals to 1, we get f dash 1 equals to 1 over 2. Differentiating f dash x again with respect to x, as we have f dash x equals to 1 over 1 plus x. Differentiating this with respect to x, we get f double dash x equals to minus 1 upon 1 plus x whole square. Putting x equals to 1 on both sides, we get f double dash 1 equals to minus 1 by 4. Differentiating second order derivative, again with respect to x, we get f triple dash x equals to 2 upon 1 plus x whole cube, or putting x equals to 1, we get f triple dash 1 equals to 1 by 4. Putting above values in equation 2, we get log 1 plus x equals to log 2 plus 1 over factorial 1 x minus 1 into value of f dash 1, which is half, plus 1 over factorial 2 x minus 1 whole square into value of f double dash 1, which is minus 1 by 4, plus 1 over factorial 3 x minus 1 whole cube, value of third order derivative at x barabar 1, which is 1 by 4. Simplifying, we get expansion of log 1 plus x in powers of x minus 1 h. Log 1 plus x equals to log 2 plus 1 by 2 x minus 1 minus 1 by 8 x minus 1 whole square plus 1 by 24 x minus 1 whole cube plus up to so on. Thank you.